A very good evening to everyone in India and a very good morning to those who are joining us from North America. My name is Dr. Himanshu Tyagi. I am Associate Professor in Mechanical Engineering at IIT Ropar, and it is a great honor for me to introduce Professor Varanasi today. Professor Kripa Varanasi is Professor of Mechanical Engineering at MIT. He received his BTech degree from IIT Madras and his master's and PhD degrees from MIT. Prior to joining MIT as a faculty member, he was a lead researcher and project leader at the GE Global Research Center, where he received many awards for his work, including Best Patent, Best Technology Project, and Leadership Award. At MIT, the focus of his work is in understanding the physico-chemical phenomena at interfaces and developing novel materials, devices, and products that can dramatically enhance performance in energy, water, agriculture, transportation, medical, and consumer devices. He is passionate about entrepreneurship and translating technologies from lab to market. He has co founded multiple companies and received several prestigious awards. A few of them I'll list over here are as follows: the DOE National Clean Tech University Prize, NSF Career Award, DARPA Young Faculty Award, ASME Heat Transfer Award, Boston Business Journal's 40 Under 40 Award, and ASME Award for Outstanding Achievements in Mechanical Engineering. Today, he will deliver a keynote lecture titled Interfacial Engineering Across Scales, a ubiquitous paradigm for energy innovation. Please join me in welcoming Professor Varanasi.
Thank you so much for that kind introduction. And it's a pleasure to be here at my alum, IIT Madras, where I've learned engineering for, after high school. So it's great to be here and talking to all of you. As Himanshu mentioned, my work is on interfaces, which is essentially the boundary between phases of matter and where all the interesting things happen, including mass, momentum, charge, energy transfer. So today give you a few examples of what we've been up to over the past several years. Um, this is a very busy slide, but kind of shows how interfaces are ubiquitous across many industries, whether it's energy or power generation, oil and gas to renewables, and our work has touched a lot of these areas. And some of our recent work has been in the CO2 and hydrogen space, and then also things like in the medical area, where we are looking at injectability of high concentration biologics to remediation of biofilms. And in agriculture, we've been looking at reducing pesticide usage and pesticides reducing the amount of pesticide pollution. And also at the energy water nexus, we are able to sort of capture this water that's given out of cooling towers, among other things. So while I will not be able to cover all these topics, I'll choose few of them, and I realize that I have only half an hour today. So I'll try to see what I can get done. Just quickly, as a group, we are very multidisciplinary. We work on a variety of topics ranging from thermal fluids to electrochemistry, and think about scale up and manufacturing so that we can take things to market. And these are few of the companies that I co-founded with my former students, including Liquid Glide, Infinite Cooling, and more recently Axon, where we are trying to reduce this pesticide pollution. As I said, the focus today is on energy, and we'll talk about energy sort of efficiency enhancements that one could achieve by fundamentally tailoring interfaces. And if there is time left, I will also talk about a project on energy water nexus and capturing water from the plumes of cooling towers. So let's jump right in. So some of our efforts over the past, last 10 years have been really to tailor interfaces, whether it's to reduce reduce wetting of surfaces, such as in this case, bouncing droplets, where we've been able to sort of overcome certain theoretical limits and go to points where you can bounce off liquids at extremely short time scales. To phase transitions such as condensation and boiling and freezing here, and crystallization, and controlling these phenomena by tailoring sort of surface chemistry and morphology, and also creating these sort of slippery interfaces where we've been able to show that we can actually tailor surfaces for a wide range of viscous fluids. For example, here there's a ketchup bottle where we can empty every last bit in the container to here a crude oil that is in a container which can basically wet anything, and we are able to sort of dispense every last drop so there is no wastage of the product. Um, and um, and examples here show ultra thin coatings that we've been able to make that can be used on condenser surfaces to promote what's called dropwise condensation, to even coating fabrics, conformally coating every fibers to be able to kind of create this non-wetting fabrics using low fluorinated or environmentally friendly coating technologies. One can use these to do separations, as shown here, where you can separate oil-water emulsions to prevent icing on surfaces. So I'll try to cover some of these topics today and see how far we can get. So one of the areas that kind of got a lot of people in the surface engineering space excited was use of what are called super hydrophobic surfaces. These were inspired by lotus leaves, where you can bounce off liquids readily. Liquids don't wet because of the structure and morphology. But early on, when we did some experiments, almost now 15 years ago or so, 15, 16 years ago, we were trying to understand how we could use these surfaces, for example, heat transfer application like condensation or in freezing. And as you can see, these are experiments done in a what's called an environmental SEM, where you can see nucleation and growth of droplets. And you see that they are actually impale these structures, and they're able, and these surfaces which are actually are hydrophobic for macroscopic droplets, basically transition and become wetting for a nucleating drop or a frost that's kind of building up on surfaces. So the same thing kind of happens when you go to a low surface tension fluid. If you take a low surface tension fluid, it can actually easily wet these surfaces. So the question was, how do we kind of go about this and make this, in fact, robust to a wide range of fluids? And this, we've only talked about also Newtonian fluids so far. If we go to non-Newtonian fluids, how do you make this sort of stable? And in a condensation kind of an application, how do you then promote dropwise condensation without having to be limited by kind of infiltration of these surfaces? So that led to this sort of a new paradigm in thinking about surfaces that can be non-wetting to a whole range of fluids. And so sticking of viscous fluids such as consumer products, whether it's lotions or food or toothpaste, to fluids in energy space, whether it's oil and gas fluids or things like flow batteries, or in manufacturing or medical, we are surrounded by these sort of viscous fluids. And the basic sort of this no slip boundary condition essentially makes all these things stick to things, to the containers they are in. And that leads to actually enormous amount of waste. Believe it or not, like almost like 50 billion packages are sold every day. And if you look at all the waste that's remaining in that, that will fill up probably 100,000 trucks. And so there's a significant amount of waste that happens because we simply can't dispense every last drop. So here we sort of developed a technology which where we take a textured surface and we are able to impregnate that with ultra thin liquid films, and these liquid films are held there by capillarity and intermolecular forces, and that allows us to then causes the products to easily slip off of these surfaces. And you are seeing examples here of this ketchup bottle and toothpaste. So the way this technology works, as I just described, you take surfaces like these and you kind of create a liquid surface, which or a liquid solid composite, the solid allowing to stabilize the liquid, and the product essentially now slips on the surface. So, the while this may seem very simple, the thermodynamics of this is fairly complex, and I'll not go through this in detail. If you're interested, there is a paper here which talks about this in detail. This system has about 12 different thermodynamic states, of which only few where we are able to kind of cause this liquid film to essentially spread atop these features in the presence of the product, as shown here in these three kind of scenarios, helps to retain this sort of a stable thermodynamic film that then is able to cause have this sort of high mobility properties. And if you're able to do that, then you can really kind of engineer products that can have this feature. You can, if you don't do this right, you can also end up in a scenario where this liquid that's sort of impregnated here can be displaced by the product, and then you got a very sticky situation in hand. So I'll show you a few examples of what we did with this. So we had this technology, we knew that this is going to, we could apply this in a whole range of products, and we were thinking of sort of commercializing this. And one of the things that came up was, hey, my wife was actually trying to get honey out of a bottle, and she said, why don't you apply it to this? And that led us to think about bottles and products, consumer products in containers. And as you can see, we were able to sort of design here a surface which is entirely made of edible materials that then can dispense every last drop. So we took this and tried this on a number of different different materials, and soon I started finding that there's about average of about 5 to 10% of, in some cases significantly high, 25% of the product could be lost, and this is sort of ubiquitous. So the great thing about this technology is, it could be designed for a whole range of products. And you see here, very difficult, sticky things, including, in this case, peanut butter, which sticks to pretty much everything. One could create a squeeze bottle that you see here. So when we actually went and sort of released some of these, the press went kind of crazy because they found this to be a very interesting story. I'll let you watch this.
Look at that thing slide. Amazing. Oh my God. Our long national nightmare is over. Mechanical engineering students
This was
at MIT
a few
come up
years
with
ago.
a super slippery coating that makes anything from ketchup to mayonnaise practically leap out of a bottle coated with the stuff. They call it liquid glide. Even Tony Soprano would be beholden to these students. Look how annoyed Tony gets at the dreaded ketchup clog.
And if Colin starts talking, homicide.
Liquid glide, let it slide. No more banging with shoes or mallets or sucking up ketchup. For traditional bottles, liquid glide could mean their last gasp. CNN, New York.
So, so this was great, and the amazing thing about this platform is because there's a solid liquid combination, it opens up the design space for for coatings or for surfaces that you'd normally not be able to do with just a solid sort of counterpart. And so for we don't invent any new chemistries. It's actually kind of putting together already available safe materials for different applications. For food, we can make these coatings out of food-based materials. For skincare, one could use dermatologically safe materials. So it's a very sort of a flexible, ubiquitous paradigm. And the other thing was we also worked on how to sort of manufacture and scale this upfront as we were developing the science. And here is sort of some early scale prototypes where we've been able to make these coatings very easily by using spray-based techniques. And today, we can do this in several hundreds of bottles per minute. So I'm just going to skip this, but very initially we also took this to market and have people react about this, and they were all very favorable and really wanted the product. So all of that led us to start this company, and we were able to then start looking at ways to scale up and take this sort of forward. So we applied this again to a range of different products. And very recently, I'm glad to say that we actually launched with Colgate. And for the first time, the toothpaste has been sold in laminate tubes for more than a century. And these laminate tubes, things stick to them. But also more importantly, they are not recyclable. So that ends up in a landfill. Here for the first time, there is a fully recyclable and completely transparent sort of a uh, uh, toothpaste tube that not only gets you to every last drop, but also is fully recyclable and meets some of the sustainability goals for Colgate. So they've been sort of very excited. This has been received very well. This launched in Europe and will come to other countries, but kind of shows how we went from some basic science and experiments in the lab all the way to market, and we're able to launch this product and put it on the shelf. This sort of won a number of awards in the packaging space, and Colgate has been extremely happy with this product. And we are taking this to other things like cosmetic packaging and so on. So kind of coming back to the bottom line, we can actually get rid of this. And what that means is when you're looking at sustainability, the amount of carbon footprint left in all that wasted product, no one even thinks about that. So we can save all of that. And also when you think about sort of recycling, when you leave a product behind, the package is not easy to recycle. So you have to wash it out, and there's a significant water footprint. So our goal here is, with this technology, we are able to sort of really reduce the CO2 and water footprint by eliminating waste. But also one can concentrate products and thereby reduce the amount of water that you're shipping around. Most of the times products have to be diluted because it's easy to dispense. But by using this technology, we can actually make concentrated products and simplify all of this plastic packaging. So there are a number of other applications of this, whether it's in manufacturing. Here you can see we can take this and apply this to large containers, where in this case paint is being dispensed, and in a traditional case you have paint stuck here, so you have to use water to clean it, and that water comes out as wastewater and it has to be dispensed. But with this technology, you can get every last bit of the product, and you don't have to clean these surfaces. One could also reduce friction drag in pipes. So here you can see that by applying this technology, highly viscous products can actually be passed through pipes, and you can reduce friction and thereby pumping power and significant power savings in pumping. Here is an example where we use this technology in flow batteries, where the interesting thing in a flow battery is where you're using the electrodes of both liquids, and the capacity increases when you increase certain ingredients, such as carbon black here. But when you do that, these liquids become basically semi-solids and they don't flow. And that's a big limitation for these. But again, by using these surfaces, which are now both have to be slippery and electrochemically stable, we can create these sort of flow batteries where you can actually flow the flow electrode even when it becomes highly viscous, and you're able to then increase its performance and capacity. We've used these technologies again to reduce the amount of reduce adhesion. In this case, we are showing adhesion of ice and adhesion of hydrates. Hydrates are basically methane that's trapped in a ice sort of a lattice. And again, if this sort of forms in a pipeline, it can essentially block and can lead to catastrophic failures of the pipeline. Of course, with icing, that leads to other issues, and it's a major problem, for example, here in the US. So technologies that can reduce ice buildup or hydrate is something that we've shown that this technology could be used to. Another important area is fouling. Here I'm showing you scale buildup on pipelines. This happens essentially from basically precipitation of salts of inorganic scale. And this kind of a fouling is significant in heat exchangers and others, and a major cause for efficiency loss. It's so much so that it almost accounts for 0.25% of the GDP of industrialized countries. So if you were to reduce this fouling, then that has a significant impact in a number of industries. And the use of this technology, where we can actually use this liquid infused surface, what it does is it creates sort of this liquid surface, which is perfect in the sense that it doesn't, it actually prevents nucleation, because almost a perfect surface. And then if there is any nucleation or buildup, that could also be removed easily because there is poor adhesion. So we have shown, for example, in this case, you can see this is control, and here you can you can completely avoid the buildup of scale. Another interesting study that we did recently was when you use the right kind of nanotextures, as in this case, this is a evaporating saline drop. But what happens is you can actually control crystallization, or sort of confine it to certain points. And there is prevention of lateral growth of crystals. And once that happens, it can actually cause crystals to actually self-eject from surfaces. So in this case, you can see this crystal actually, or this fouling material, which would have normally easily fouled the surface, is able to grow legs and is able to self-eject. And since this looks like a weird bug, we named it a crystal critter. So by using temperature, you can do some interesting things. In this case, you can actually create a temperature gradient and cause these legs to form, and kind of cause this this critter to actually move away from one end to the other end in a way that it kind of almost this fouling material ejects itself and walks away from the surface. So we were able to also create some interesting, if you're into Star Wars, this looks like a AT-AT walker. Shows that we are kind of having fun doing science as well. You can also then create active surfaces. So here, by using active liquids, in this case, ferrofluid impregnated surfaces, applying a magnetic field, one can actually then propel liquids forward. Another interesting thing with these surfaces is, because they have very little adhesion, even when you apply a thermal gradient, you can actually induce what's called thermocapillary forces. And we were able to see pretty high velocities that are unlike anything for a thermocapillary effect. So we are able to get to millimeter per second kind of velocities of a droplet. And very recently, we saw some other interesting effects where here you can see that the top is a regular sort of a Leidenfrost case. And here, when you put a liquid on this, let me actually play this again. When you put the liquid here on this oily surface, counterintuitively, because you would say that you have a viscous film, you should have higher friction, but in fact, it actually propels forward much more at a much higher velocity. And this is, in fact, there's a very cool coupling of thermal and momentum boundary layers at disparate time scales. It's a very interesting effect, which of course, the limited time I'm not able to kind of go through. And one can then use these technologies for applications like heat exchangers, whether it's steam cycles or liquefaction or refrigeration. We have condensers and boilers, and if you look at condensers, and if you look at power generation in general, almost 85% of all kinds of the install base that you have today uses steam turbines for conversion. And one of the key things, of course, you have your condensers and boilers, and in all of these cases, you have in this case a condenser tube, a water film or a liquid film forms on the surface, and that leads to a resistance for heat transfer. And as you can see here, the film becomes a resistance, but you're able to shed these as drops, which has been researched for a long time. Then you can get significant increases in heat transfer, and we've been able to show almost 7 to 10x increases. But the key point here is, why is this technology not applied across industry? And the issue here is that you have challenges to durability and manufacturability. And what I mean by that is, if you take a regular industrial condenser like this, you can see these tubes are just like slammed into these slots, and these things are pretty large in scale. And coating a tube one by one, doesn't actually make economic sense. And if you go to condensers like these, which are in oil and gas, they have crazy shapes, and it's almost like you can't even coat them, and you can't even take these tubes out. So you should be able to like do this in situ and on a retrofit basis. So, and as I mentioned earlier, if you just used a super hydrophobic surface, it's not going to really work because you'll end up forming these films. And if you do these liquid infused surfaces, you can get certain amount of robustness, and you can, maybe spray coat these surfaces. But even then, the issue is, the durability and longevity over a long period, almost like 5 years or something. And we have shown that you can actually take this and apply this to low surface tension fluids as well. And knowing all these issues, we actually developed a totally different technology. And this is using actually room temperature vapor deposition, where we are able to create less than 100 nanometer films that can then be applied to a range of surfaces, because this system can actually conformally coat these tubes or other heat exchange surfaces. So that led to pretty robust way to do this dropwise condensation, and could also be applied to things like in this case very low surface tension fluids. Low surface tension fluids are notoriously hard to condense in a dropwise manner because they would want to spread on any surface. But by creating low hysteresis, we are able to go to dropwise for even these kinds of systems and actually boost heat transfer quite significantly. So the key is, how good is good? And what you find is that in terms of the efficiency gain, because there's the condenser resistance is one side, but there's also the coolant. So eventually, you can reduce this, the other side starts to catch up. So there's really, no point going to significantly high gains in heat transfer because the other side will catch up. And so, one could stay essentially in that zone where you could, get almost 3 to 4x increase, and that's actually pretty good enough. So I'll kind of switch gears, I think, in the last few minutes to boiling. This is an example of a Leidenfrost drop, which, as you all see probably in your kitchen, when you heat up a surface, the drop sort of bounces off on a hot surface. And what we have done is, and that actually limits cooling, and we have created sort of super hydrophilic nanotextures, in fact, a hybrid surface that allows for liquid to actually adhere. And the key point here is, if you make these dense nanotextures, it doesn't work because the vapor pressure will actually kick the droplets off. So what you want is a hierarchical surface where you allow for vapor escape while causing wetting of such a liquid. And if you take this to things like pool boiling, we've been able to show some nice studies using simultaneous sort of high speed and IR camera, visualizing these these sort of boiling bubbles. And we're able to show that you can get, again, a significant increase in VHF with texturing because it helps re-wetting the liquid. But there is a limit to that, in the sense that, you should be able to re-wet the surface before, a dry patch can grow. And what's limiting the re-wetting is actually the viscous resistance also posed by by the surface textures. So capillarity is helping to wick, but viscous resistance will kind of prevent you from getting there. And then lastly, the use of, let's say, if I use saline droplets. So when people look at boiling, one looks at pretty clean DI water or clean liquids. But actually our real surfaces are not, or real fluids are not that clean. And so here what we have shown is that if you actually use say even little bit of say foulant, like in this case is salt, the CHF dramatically drops. And that's because you get sort of these crystallization and deposits of fouling layers built up. And that leads to actually pinning of bubbles and growing of hotspots. So counterintuitively here, we actually found that if you actually go to a hydrophobic surface, which is not good from a bubble perspective because it will actually hold the vapor, it actually kind of creates a region where you don't have supersaturation or buildup of scale in this case. And by using sort of a hybrid biphilic surface, you can then kind of promote a situation where you can reduce sort of the buildup of these foulants. And so can actually then in a real scenario give you enhancement and prevent any CHF issues. So I don't know how much time I have. I think probably am I done?
Yeah, if you want, you can take few minutes. That's fine.
Okay, so what I will do is I'll just go to another technology real quick and maybe stop there. So another area that we worked on is you look at cooling towers, or every power plant needs cooling, and in this case, people have stopped just using a lake or a reservoir as a system where you can just dump back hot fluid. So people use cooling towers, and instead of being once through, the cooling happens through a tower like this. And you see this sort of white smoke, and people think it is pollution, but that's actually, demineralized water going out there. So what we have done in this case is actually capture those plumes. And believe it or not, like about 40% of total freshwater withdrawals in the US happens, is earmarked for power. And globally, about 3 trillion gallons of fresh water goes through these cooling towers. And if you take like a 600 megawatt, a single 600 megawatt power plant, it uses as much water as 100,000 people could use. That's about 1,000 million gallons of water. And this also costs a significant amount of money for the power plant. And in some cases, people are not allowed to do plumes. For example, if you're near an airport or an urban area. So what we have done is, hey, this is a great place. If you're able to capture those plumes, that can have a significant impact on the energy water nexus problem. And in fact, the water problem that is a global water scarcity problem. So what we have done is built up a mock cooling tower in the lab. And these kind of plume droplets that you see are very, very tiny. They're about in the tens of microns scale. And so to be able to do this, we actually developed a technology where we inject charge. And by injecting charge, we create a different force, an electrical force. So you see here on this video, which, let me actually go back. So this video, what you see is we have used, so the same plume that's coming out, and we have a coffee strainer as a mock-up, but we will switch on the electric field and you see that the plume disappears and all of that water is now sort of captured and is able to be drained back and collected. And this water now is demineralized and so is extremely kind of pure. And you can then make use of this high quality water, whether you put it back into the cooling tower back, or you could use it for other purposes such as boiler feed and so on. And in places where you could use it as drinking water even. So what's happening here in a nutshell is, people use meshes and so on to capture fog, and the efficiency of these systems is extremely poor because these droplets that you see here follow the wind. And this is a illustration of a single mesh wire. So the drops actually go through and only captured through inertial contact. And so that leads to a lot of these drops actually go by. And so the efficiency of such fog collectors is about only 1%. So what we have done is by injecting charge, we are able to create a new force that essentially takes these and brings them back to the collector. There's an electrical force driving them. And you can see that a significant fraction, almost double the size of this mesh wire, where drops that are going away are making a U-turn and coming back and are getting sort of captured. So we developed this technology, and I'm going to play this one last time. And you can see that this fog that is happening or coming out of this cooling tower is being able to capture, is getting captured by this charge injection and sort of a electrical force. So what we did was we then actually went and formed a company to commercialize this technology. And the bottom line is, say we go back to the combined cycle plant, we could be saving about 150 million gallons of water. And that's about $1 million in savings for the power plant with only very little energy usage, and we can be eliminating plumes. So again, this is a company that we founded with my students, and we actually applied this technology, on a MIT power plant to kind of prove this out before we formed the company. And we have been, sort of successful and made this work. For example, here is the one of the MIT power plants. It is a nuclear research lab at MIT that also has a cooling tower and plumes. So we are able to show this at scale, and now we are deploying this across power plants in the country. And I leave with this final note that what's happening here is, if you take countries, there are power plants along the coasts of countries which use seawater for cooling. And if you were to use our technology, then all the sort of desalination is already being done for you, because you're already heating up the water and you're basically doing evaporative cooling. So the droplets that are, or the plumes that are coming out of the cooling towers is actually fresh water. So we just have to capture them. And so when you compare our technologies, the company that we founded is called Infinite Cooling, to traditional desalination, RO desalination, we are about 100 times lower in power consumption and low OPEX costs. And importantly, we can then apply these to power plants, and these power plants can become combined power and water, and can significantly disrupt the desalination kind of space. And so, for example, I don't know if you heard about this Cape Town case a few years ago where they ran out of water. And to avoid this, they built like a desalination plant where the cost of water is about $12 per kilogal. There is a nuclear power plant about 15 miles from the city. And if we were to do this infinite cooling kind of a technology, we'd be at 8x lower cost and 75% more production of water, because all the waste heat is already being used there to evaporate water and purify it, and all we have to do is just collect that. So that's infinite cooling, and with that I'm going to pause and happy to take any questions.
Thank you very much, Professor Varanasi, for giving such a wonderful talk where you gave very nice images and videos which were very nicely explain the concept that you are doing in the lab. Thank you very much. Now I invite questions from the audience members. I believe there is a Q&A tab where all the members can see in the conference website. So this is a Q&A just below the video. So you can go ahead and type your questions, and then we will be able to see them over here. Till that happens, I would like to ask maybe a few questions. So
Sure.
What you are doing from the last part, I will ask first regarding the
Yeah.
plume. So this is essentially just like we are getting the precipitation, just like it happens in the rain. So we are getting that quality of water, isn't it?
Yeah. So when you take Yeah. So basically, because you're doing evaporative cooling, the vapor, the drops evaporate, the vapor comes out, mixes with the cold air, and becomes, kind of precipitates and forms these fog droplets. So yes, so it's demineralized water. It depends, of course, on the surrounding. If the air is polluted, you may have, some pollutants in the water, but that could be purified, much better than starting from, say, seawater or other sources of water. So we have seen, for example, in Cambridge here right next to MIT, the water we collected. So this system here uses city water, and the water we collected was almost like 100 times purer than city water.
Yeah,
So yeah.
that is true. So as long as it doesn't mix with the chimney exhaust, which is probably very far away, then it is very ultra pure water, right?
Yeah, and we are collecting it right there. So we so there should not be any too
Yes,
much of
yes,
mixing, but
right,
one could then figure out a way to prevent things to mix if that's a concern.
yes, yes. So now a lot of questions are coming over here. So let me go ahead. Are you able to read the questions yourself, or do you want me to go ahead
Oh,
and
let
read
me
them?
see. Let me see.
Yeah.
Yeah, I can see the questions.
Yeah.
So I see, one question from on regarding slippery coatings. Can they have any possibility of causing health concerns for food and beverages? Yeah, that's an excellent question. And so precisely because of that, we can actually tailor the because this is this liquid solid composite, we use already existing safe materials that are approved already by from a safety point of view from the respective industries. So for food, we can use food, basically the coatings are made out of food or ingredients in the product itself. For again cosmetics or beauty products, you can make it again out of ingredients that are already in the product. So that's essentially the point, is that it gives you such a nice platform that you can make it out of safe materials. The second question that I see here is, can electric field be beneficial for interfacial evaporation? Again, it depends on what you're trying to do. If you apply an electric field, are you, to evaporate, are you, you need to be able to create some sort of a, create a flux. And so if you're using an electric field to to maybe get these droplets to swirl and increase flow, you should be able to enhance evaporation. But intrinsically, I'm not entirely sure how that will help.
Thank you very
Uh,
much. So one
I have
more.
there's
Yes,
one
yes.
more question, and I think that's about dropwise condensation. Is there any deterioration in the long-term usage? Yeah, and again, that's an excellent point. So when we did, for example, when you take super hydrophobic type surfaces and you go to length scales where you can make it, very small, you can get this effect called jumping droplets. So in those cases, when the drops actually combine and jump off, they can actually cause over time, if your modifier is not good, it can actually cause deterioration, which is actually why we did the ICVD technique, where in the ICVD case, we actually covalently bond our surfaces to the baseline heat exchange surface. And by doing that, we actually enhance durability. So our accelerated tests, we were able to show that we can be at around 5 years of life of these coatings, which is kind of what these people look for.
Thank you. Thank you. There's one more question in the chat where a student asks, can we increase electric potential technique in solar still for desalination? So I think it's
Uh,
kind of proposing the similar thing what you're showing for the plume. So I think the same can be applied there.
yeah. I mean, I think definitely, yes. And then I saw there's another question: can the plume
Yes.
connection be extended to restaurants if it is so cost friendly? I didn't quite understand that. Uh, so
Maybe
you,
he has mixed it. I think in restaurant, I don't think there is the cooling tower effect, right? or is it?
So, I mean, so I think, so where this becomes important is if you take cooling, like if you take buildings and cooling of buildings, if you have like really large buildings and malls, they use also cooling towers. And there you can see plumes, and we are actually working with a number of such people. And also data centers, for example, where they have to have cooling. That's another area. So yeah,
So wherever there is this mist and fog effect happening in a
exactly. Wherever you
concentrated
have
region.
plumes, so again, certain regions you won't get plumes, and so our technology doesn't apply there. This particular technology.
And if you have time, maybe one more question has come from Soham Goswami.
Yes, yeah, and he's saying how feasible is it to use charge injection in harvesting natural fog, considering much lower water, how energetically expensive? So yeah, so that's again a great question. Indeed, yeah, we can actually use this for natural fog and actually improve. And you see that with our technique, we went from that 1% to 5% efficiency for
Yes.
natural fog collectors to 100%. So you can significantly increase the efficiency. In terms of cost and so on, the electrical power that's needed is extremely low. So that's what makes this very attractive, because we are, while we use, we ionize and we create the charge injection, the currents are extremely low. So, we are looking at something like, 50 watts per meter square or something like that. So again, very low. That could be powered, for example, with a solar panel
Yes.
next to these kind of collectors.
Right. And maybe there could be some security and safety implications also in the positive way. Like in North India, every winter we have this visibility issue related
Yes,
to landing of planes and even railways. They are looking at these kind of things. So maybe in future,
absolutely.
if it can be scaled with large meters and several meters, maybe there is potential there. It's fantastic.
Absolutely. In fact, we are working on a project, or the company is working on the project on, there's specific, exactly this issue. The plumes actually make it very dangerous in some places. So in that case, the application, this is at a power plant in UK. They don't want plumes. They don't. They want to eliminate these plumes. More so coming at it from a safety perspective.
Thank you. I think their presentation was very well received and students asked very nice questions. And I think we can conclude now. And I thank Dr. Varanasi once again for delivering such a nice talk. We are very grateful for your presence. Thank you very much.
Thank you so much. It's always fun to be back at my alma mater. So it's a great pleasure for me as well. Thank you so much.
Thank you.
Bye.
Bye-bye. So with that, we conclude this particular session, and our conference is still continuing tomorrow. So I request all the delegates that tomorrow, India time, 9 o'clock, please join the next sessions. With that, I thank our distinguished speaker and all the participants as well as the student volunteer. Thank you.
HMTC organizing team thanks Professor Kripa Varanasi for his insightful keynote talk and Professor Himanshu Tyagi for chairing the session. We thank all the authors and audience for their participation. The session 1 officially ends now. Thank you.